Welcome to another edition of Coonrod's Corner. Today's topic, AD300C Antenna Grade Laminates Overview. Now here's your host, John Coonrod.
Hello, welcome to Coonrod's Corner. My name is John Coonrod and I am a Technical Marketing Manager for Rogers Corporation. Today I'm going to spend some time and talk about the AD300C product family, and this is a product that's been around for many years. It's very well established and has a very successful history in cellular base station applications, and specifically as PCB-based antennas. Now this material is a PTFE woven glass ceramic filled material. It's very low loss. It's good for high thermal conductivity, and also it's very good for PIM, passive intermodulation. I'm going to talk about that a little bit later. What's shown here is a portion of the datasheet for the AD300C materials, and a few things I'd like to point out. First off, the dielectric constant of 2.97. That particular value is not by mistake. That's formulated very specifically because there's more and more antenna applications targeting that dielectric constant number. Now if you look at the dissipation factor at 10 gigahertz, a dissipation factor of 0.002 at 10 gigahertz is considered very low loss. And then the TCDK, which here is noted as TC epsilon sub r, that's basically how much the dielectric constant will change with a change in temperature. And a TCDK of 50 parts per million per degree C or less, as an absolute value anyway, is considered very good. And in this case, the AD300C materials has a minus 25 parts per million per degree C TCDK. That's considered extremely good, as a matter of fact. Now the CTE is 9 and 15 in the XY plane, and the copper CTE that you'd want to match it to is 17. So this is very closely matched to copper, and that does add to the reliability for a multilayer. Also the Z-axis is 54, which is not uncommon. Most materials in the Z-axis are a little higher for CTE, and 54 is not a bad number. As a rule of thumb, 60 parts per million per degree C or less is considered good for a laminate to be used in a multilayer circuit fabrication. Now also moisture absorption here at 0.06, that's also considered extremely low and very good. And then finally thermal conductivity of 0.5 watt per meter K is also a very good number. Control of the dielectric constant is very important for antenna applications, and in the case of the AD300C materials, the dielectric constant is controlled to a tolerance of plus or minus 0.05. That's considered very good. And now there's other issues to think about with dielectric constant as well, and one is dispersion. Dispersion is how much the dielectric constant will change with a change in frequency. Now all materials have dispersion. However, in the case of AD300C, you'll find it has very minimal dispersion, which is good. And that's one reason why this material is used in wideband applications where the dielectric constant has to be constant over a wide range of frequencies. In this graph, I'm showing testing that I did with 50 ohm microstrip transmission lines. The test method is using a differential phase length method. And I'm looking at the response from 0.1 gigahertz, or in other words 100 megahertz, up to 5 gigahertz. And you can see the dielectric constant does not change much. So across that wide range of frequencies, there's a change of actually less than 2%. I think it's about 1.6%. So that's a very little change. So that basically means that the dielectric constant does not change much with a change in frequency, and that means it's got very well-behaved dispersion, and that's a very good attribute for any material used in antenna applications. Insertion loss is another topic that's very important for antennas. Basically having material that generates less insertion loss in circuit form means that the antenna is a little bit more efficient. Also you can handle higher powers a little bit easier, thermal management's a little easier to deal with. And then also you have the feed lines, of course, that's going to feed the energy to the radiating elements. And if these feed lines have lower loss, that means your radiating elements will actually receive that much more power. So overall it's just a good efficiency for the antenna. In the chart I'm showing here, we're looking at insertion loss of a microstrip transmission line and using the differential length method. And here I'm going from about 10 megahertz to 5 gigahertz. And you can see that the insertion loss is very well behaved, and going out to 5 gigahertz you can also see that the losses are very low. A number of 0.06 dB per inch is considered a very low loss insertion loss for a material. PIM is another issue that is very difficult with antenna applications. PIM is an abbreviation for passive intermodulation. It's a rather difficult topic when you get into the details. It's also kind of difficult to measure. However, this material, the AD300C, has been measured for PIM performance routinely here at Rogers and also with the customers that use this material. And this material is found to have very low and very consistent PIM. In this chart, what I'm showing is the PIM performance of a microstrip transmission line that was tested using 60 mil AD300C laminates. The transmission line is actually a long transmission line, 12 inches long or 300 millimeter, and it was tested with a PIM tester that is a dual tone tester, about 1.9 gigahertz and about 30 watts of power being applied. And in this particular case, the x-axis is time, and what we did was we looked at the PIM performance of this circuit over 55 seconds, and at each second there's actually 10 data points being collected. So this is actually a collection of 550 data points. And if you're used to looking at PIM results, this is going to look a little unusual because it is very well behaved and there's very little differences in these different results. Normally PIM has a little bit more noise, and that's kind of the nature of the beast when you're trying to measure something with that low of a number. Essentially though, years ago, a PIM value of minus 145 dBc was considered good. Nowadays, as technology has evolved, a better number, minus 150 dBc, is really desired. And in this case for PIM, a negative number that is larger is actually better. And even more recently, the latest technology that's being worked on with antenna applications is a PIM value of minus 153 dBc that's really starting to be demanded, and that's a very difficult number to achieve. Now what's shown here is the material is, again, 60 mil AD300C. It's a microstrip transmission line we're testing, and you can see the PIM performance is going somewhere between minus 162 and minus 167 dBc, and those PIM values are considered extremely good, and also you can see it's very consistent across this measurement that we took over 55 seconds. On the Rogers webpage for the AD300C, there is additional information. Of course, there's data sheets there, which we talked about briefly. There's also processing guidelines, and there's more information on antennas and PIM performance. The brochure that's on our webpage that is called PIM and PCB Antennas has additional information on the antenna applications where PIM is critical, and it also gives you some of the material properties of the AD300C and how it performs with these different applications. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.